Hi everyone, my name is Allie Lewis and I'm a PhD candidate at the University of South Carolina. And today I'm going to talk to you about a project that I've been working on titled Corticospinal Tract Fractional Anisotropy Extracted from Native versus Standard Space in Chronic Stroke. So I'm going to start with a little background. So we know that the corticospinal tract, or the CST for short, is important for the control of movement. And we also know that it can be damaged or degraded after a person has a stroke. We can measure the integrity of the CST using neuroimaging techniques. And specifically, we calculate a number called fractional anisotropy, or FA. This FA number really tells us about the quality of the white matter tract, or the integrity of the white matter tract. So when we're thinking about movement after stroke, we're often most concerned with the integrity of the CST. In addition, researchers have been relating FA of the CST back to motor function or motor impairment in people with stroke. However, there are many different methods and approaches to measuring FA, and a gold standard for how we measure this has not really been established in the field. So one of the nuances in the measurement of corticospinal tract FA is that we can extract the data from different spaces. So in brain imaging, we really have two spaces. So if you picture my brain as a 3D shape and your brain as a 3D shape, they might be slightly different. So when we acquire data in this scanner, we acquire it in your own brain space, where all the little data points are mapped onto the specific shape of your brain. And we call this native brain space. The second kind of brain space is called standard space. And this is when we take your brain data that we acquire in the scanner and we map it onto a standard template brain shape, which is the average shape of a bunch of different people's brains. So that kind of brings us to the purpose of the study. So because there is no gold standard for how FA is measured, different researchers in different labs do this in different ways. So some present data in native brain space, while others present data in standard brain space. So we really wanted to understand how this extraction space might affect FA values in individuals who have had a stroke. So here we are at methods. So we had 24 individuals in the chronic phase of stroke. They had on average mild to moderate upper extremity impairment. And then you can see at the bottom there is a depiction of all the subject's brain lesions overlaid. Here are the methods from the paper. This is a lot of words, so I'm going to make it really simple. All of our participants underwent imaging, and then we used 3 different commonly used approaches for capturing the CST. We used a cerebral peduncle approach here, where we drew a mask on 3 adjacent slices in the cerebral peduncle. We used a probabilistic tract approach, where we drew tracts from the cortex to the CP in each person, and then we used a tract template approach, where we used a template from a published template of the corticospinal tract. And then we extracted FA values from both standard and native space. So here we are looking at results. So what you're looking at here is by approach. So we have the cerebral peduncle approach here, the probabilistic tract approach here, and then the tract template approach here. Now these bar graphs are by subject. So here's our 24 subjects on this axis. And then on this axis, we have the FA standard values minus the FA native values. So bars that fall to the right mean that for that subject, the FA standard value was higher than the FA native value. And you can see that for all 3 approaches here, in general, FA standard was higher than FA native. And then here we have the mean absolute difference. And so while FA standard was higher than FA native, it was by a relatively small magnitude, considering that mean values for this population for the ipsilesional tract are between 0.4 and 0.5. And then finally, we wanted to look at how extraction space might impact relationships between motor impairment. So we ran correlations between the upper extremity Fugl-Meyer and the lesion side CST FA value. And what we found is that the relationship between CST FA and the upper extremity Fugl-Meyer was similar regardless of extraction space for all of the methods, where higher FA values correlated with higher upper extremity Fugl-Meyer scores. So higher FA correlated with less impairment. So in conclusion, we did find differences in FA values for the corticospinal tract between, depending on extraction space, where standard space FA values tended to be higher than native space values, although this difference, the magnitude of this difference was relatively small. We also found that relationships between the lesion side, CST, FA, and impairment were similar regardless of extraction space. And since we did find those differences in FA values, we feel that our results provide some context for how we're interpreting FA values across studies that might extract data from different spaces, and that we also might need to consider extraction space when we're aggregating data across studies. So here are our references, and we'd like to acknowledge the NIH and AHA for supporting this research. And then finally, thank you for your time. You can email me at af10@email.sc.edu with any questions. I know I glossed pretty quickly over some of our methods, so you can see more details in our publication in Human Brain Mapping. And then finally, if you're interested in any other work going on in Dr. Stewart's Motor Behavior and Neuroimaging Lab, you can see our lab website, motorlabsc.org. Thank you so much.